Chapter 6, Momentum Analysis of Flow Systems. Welcome to Chapter 6 of Fluid Mechanics 1, where we shift our focus from energy to momentum. So far, we've looked at how fluids behave in terms of pressure, velocity, and energy. But now it's time to explore how moving fluids carry and transfer momentum, and what that means for the forces acting on systems like nozzles, bends, and turbines. Momentum analysis gives us a powerful tool to predict real-life phenomena. Why does a fire hose kick back? How do turbines extract force from moving water? The answers lie in Newton's second law applied to control volumes. Get ready to turn fluid motion into quantifiable force and gain a whole new way of analyzing flow systems. 1. Newton's laws. To analyze momentum in flow systems, we begin with Newton's laws, the foundation of classical mechanics. These laws help us connect force with motion, which is exactly what we need when fluids accelerate, decelerate, or change direction. Newton's first law tells us that in the absence of a net force, a fluid element will either stay still or keep moving at constant velocity. Newton's second law gives us the math. The net force equals the rate of change of momentum expressed as F equals dmv by dt. This equation will become the core of our control volume analysis. And Newton's third law reminds us that forces come in pairs, something essential when dealing with fluid jets, nozzles, and propellers. Linear momentum is simple mass times velocity, but when the flow curves or rotates, angular momentum becomes relevant too. We'll use both concepts to derive force expressions for real-life fluid systems. 2. Choosing a control volume. Before applying momentum principles, we need to choose the right control volume. And this choice shapes how we analyze the flow. A control volume can be fixed, moving, or even deforming, and each type fits different kinds of problems. Fixed control volumes are best for stationary systems like nozzles or pipe bends, where the boundaries don't move with the flow. Moving control volumes come in when the system itself moves, like a jet engine in flight. And for cases where the boundaries stretch or shrink, like inflating balloons or combustion chambers, we use deforming control volumes. Choosing the right type of control volume helps simplify the math, capture the right physics, and avoid confusion. Start by asking, is the system moving? Is it stretching? Your answer will guide your control volume. 3. Forces acting on a control volume. To apply Newton's second law to a control volume, we need to account for all the forces that could be influencing the fluid. These forces fall into two main categories: body forces and surface forces. Body forces act throughout the volume, like gravity pulling every fluid particle downward. Surface forces, on the other hand, act on the boundaries. Think of pressure pushing on walls or viscous shear acting along pipe surfaces. Pressure forces act perpendicular to the surface and are responsible for many flow behaviors we observe in nozzles, diffusers, and valves. Viscous forces arise due to fluid friction, resisting motion, especially near solid boundaries. Lastly, reaction forces appear at supports or interfaces with other systems. They keep everything in equilibrium when fluid momentum tries to push or pull on structures. Understanding these forces sets the stage for momentum equations. Each force has a role and none should be overlooked. 4. The linear momentum equation for a control volume. Now we bring it all together with the linear momentum equation for a control volume. This equation is built from Newton's second law and split into two terms: the rate of momentum change inside the volume and the net momentum flux crossing the boundaries. Together, they let us calculate the net force acting on a fluid system, or predict how a flow behaves under force. In steady flow, we can drop the time-dependent term and focus only on surface interactions. For unsteady flow, both terms matter. Momentum is constantly building or dropping. And if no external forces act on the system, total momentum remains conserved. But real-world velocity profiles aren't always uniform. That's where the momentum flux correction factor beta comes in. It adjusts our calculations to account for non-uniform distributions, especially in laminar and turbulent flows. For laminar flow, beta is around 4/3. For turbulent, it's only slightly above 1. Small correction, big accuracy.
5. Review of rotational motion and angular momentum. Before we learn angular momentum in fluids, let's revisit the basics of rotational motion. Just as velocity and acceleration describe linear motion, angular velocity, omega, and angular acceleration, alpha, describe how fast something is spinning and how its spin changes over time. The moment of inertia, denoted by I, tells us how much an object resists changes in its rotation. It depends on both the mass and how far that mass is from the axis of rotation. The farther the mass is distributed, the larger the moment of inertia. Torque, symbolized by m, is the rotational equivalent of force. It's what causes angular acceleration, just like force causes linear acceleration. The relationship m equals I alpha mirrors Newton's second law for rotation. These concepts help us understand fluid systems with rotation, like rotating tanks, pumps, or swirling jets. Momentum isn't just linear, it can spin, and when it does, we need these tools to describe it.
6. The angular momentum equation. Just as linear momentum connects force to motion, angular momentum connects torque to rotational motion. The angular momentum equation tells us how the rotational state of a system changes over time, and it's written as the rate of change of angular momentum equals the sum of external moments. Sigma m equals dh dt. For control volumes, we expand this into two key terms: the time rate of change of angular momentum inside the volume and the net angular momentum crossing the control surface. This is especially useful when analyzing flows in rotating systems, like turbines or propellers, where fluid motion involves circular paths. In steady flow, the time-dependent term drops out. And if no external moments act on the system, angular momentum is conserved, meaning the spin stays constant. That's the principle behind figure skaters spinning faster when pulling their arms in. Understanding angular momentum isn't just for mechanics, it's essential in fluid systems with rotation, and this equation is how we capture it. 7. Applications in fluid mechanics. Everything we've learned about momentum, both linear and angular, comes to life in rotating machines. Devices like pumps, turbines, and fans all rely on radial flow principles, where fluid moves in circular paths and transfers angular momentum to or from rotating blades. In these systems, the angular momentum equation becomes a practical design tool. It helps engineers calculate torque, which directly relates to how much power the device can generate or absorb. One of the most important tools here is Euler's turbine equation. It gives us the torque on a shaft as a function of the fluid's tangential velocity and radius at the inlet and outlet. The equation T shaft equals m open parentheses R2 V2 comma T minus R1 V1 comma T close parentheses shows that torque depends not just on how fast the fluid is moving, but where and how it enters the system. Mastering this equation is key to understanding energy conversion in fluid machinery. 8. Summary. Momentum analysis gives us the language to describe how fluids push, pull, and rotate objects in their path. The linear momentum equation connects flow with force, perfect for calculating reaction forces on bends, nozzles, and jets. Meanwhile, the angular momentum equation steps in when rotation matters, helping us analyze torque in turbines and pumps. Together, these equations explain how motion turns into mechanical output. From power generation in wind turbines to force balancing in piping systems, momentum is the invisible force that engineers must quantify. And because real flows aren't always uniform, we introduced the correction factor beta to account for velocity variations across the flow section. It's a small adjustment that ensures big accuracy. In fluid mechanics, mastering momentum means unlocking the mechanics behind real-world energy transfer. This is where theory meets application.